Alright, so today we're going to be looking at modified exponential growth and decay. So sometimes quantities change at a rate that is not directly proportional to the quantity present at time t, but rather the difference between the quantity at time t and some constant value. What that means is, if we have, for example, a cup of tea and it's sitting on a bench and it's cooling, well, the rate at which the rate at which it cools is dependent on the room temperature. Obviously, if you've got a cup of tea sitting in a freezer room, for example, it's going to cool down a lot quicker than it would in a normal room temperature room. So this type of exponential growth and decay is where the rate at which something decreases or increases is not directly proportional to the quantity. So Newton's law of cooling is the main application of this. It was invented, obviously, by Isaac Newton, and it was an application of calculus which he helped develop. Now, technically, Newton's law of cooling is not in the syllabus, but really the questions you're doing are Newton's law of cooling. They just don't tell you that. So, Newton's law of cooling, and same as population growth, says dn dt, or dt to t, is k times by some constant n minus p, or minus k some constant t minus p. Not important to focus on that because you're going to derive that each time when we do these problems. The main thing we're going to focus on is this. We can see that this is the exact same as our exponential growth and decay, except you've got a plus p out the front. So we can verify that dn dt is kn minus p is a solution to this. So if we differentiate dn n, we get k, that's a highlighter, we get k times by a e to the kt. So a e to the kt, well, if we rearrange this equation, a e to the kt would be n minus p. So if we replace this with that, we get k n minus p. And we're done. Okay. So q is equal to 6 plus 10e to the 4t. If we differentiate that, we get 4 times by 10e to the 4t. But since if we rearrange that equation for 10e to the 4t, we would get, let's get the highlighter again, we'd get 10e to the 4t equals q minus 6. So we're going to replace this with q minus 6. Same idea up here. If we differentiated this, we're going to get minus 0.7 times 14 e to the minus 0.7t. But if we rearrange this, we would get 14 e to the minus 0.7t equals t minus 56. So we're going to replace that with t minus 56. So in the first example, the rate of change of q is not proportional just to the quantity, but it's proportional to the quantity minus 6. So q minus 6. And the rate of change of t is proportional to t minus 56. So an example. If t is equal to 5 plus 10e to the minus 2t, we've got t is temperature and lowercase t is time. Find the initial temperature. Well, if we make t equal to 0, we're going to have temperature is equal to 5 plus 10 times e to the 0, which is e to the 0 is 1. So 5 plus 10 is 15 degrees Celsius. The temperature after 4 minutes, we're simply going to substitute in 4. So 5 plus 10 e to the minus 2 times 4. I think it's 15. It's going to be 15 something. E to the power of minus 2 times 8, 2 times 4, we get 5.003 degrees Celsius. Okay, part C says the temperature as T approaches infinity. There's two ways of going about this. If I substitute, say, in 100,000, 5 plus 10 e to the minus 2 times 100,000, your calculator's going to give you 5. Obviously, the answer's not actually 5. It's going to be 5 point, then a lot of zeros and some decimal. But as t approaches infinity, the reason it approaches 5 is because this graph, and we're about to graph that in a second, 10e to the minus 2t is an exponential graph, and it looks like this because you got a minus. So we can see that as time goes on, your exponential graph approaches 0. So this part of your graph that I'm going to highlight again, this part here, that approaches 0. So that means your temperature would just be 5. So t to t is simply going to be minus 2 times by 10e to the minus 2t. We rearrange that. We could say it's minus 2 times t minus 5. Okay, now we're going to draw our graph. We said that as t approaches infinity, as time approaches infinity, your temperature is not going to go below 5. So there's going to be an asymptote at 5. It's never going to reach, theoretically, it's never going to reach exactly 5 degrees. But as t approaches infinity, it's going to slowly get towards 5, or quickly get towards 5. It starts at 15, so our graph's going to look something like that. So temperature's here, time is here. Okay. Number 2, in a certain town, the growth rate is proportional. The growth rate in population is given by d n to t as k, n minus 125. Show that n is 125 plus a e to the kt is a solution to the differential equation. So at the moment, all we can do to show these solutions is by differentiating. So n dt is equal to k a e to the kt. But if we rearranged this equation for a e to the kt, we're going to get n minus 125. So we're going to replace that with n minus 125, and we get our answer done. If the population is initially 25,650 and after 5 years it's 31,100, find the population after 8 years. Okay, so we know that my equation is n, why does it keep doing that? N is 125 plus a e to the kt. So we're told it's initially 25,650, and that's 125 plus a. Now e is going to be a e to the 0 because t is 0 at this point, but we know that e to the power of 0 is 1. So a is going to be 25,650 minus 125. We get 25,525. So my new formula is n is equal to 125 plus 25,525 e to the kt. Right. After 5 years, it's now 31,100. So we're going to say 31,100 is equal to 125 plus 25,525 e to the 5 times k. All right. If we subtract 125 over, we're going to get 30,975 is equal to 25,525 e to the 5k. Divide by that, we get e to the 5k is equal to 30,975 on 25,525, and we get 1239 over 121. So that means k is equal to 1 on 5 ln of 1239 on 1021. Making that into my original equation, I get n is equal to 125 plus 25525 e to the power of 1 on 5 ln of 1239 on 1021. Now the question wants after 8 years, so we're going to times that by 8. And we get 34,913. All right, part C says, when will the population reach 40,000? All we have to do there is set 40,000 be equal to my equation. So 40,000 equals 125 plus 25525 e to the 5k. Oh no, not 5k. We all know the value of k. It's 1 on 5 ln of 1239 on 1021 times by time. If we have a go at solving that, we're going to minus 125 from both sides and then divide by 25525. I would just do that in one step on your calculator. So on the top of your fraction, it's going to be 40,000 minus 125. On the bottom, it's going to be 25525. So we get e to the power of 1 on 5 ln of 1239 over 1021 t is equal to 1595 on 1021. Taking the ln of both sides, we get 1 on 5 ln of 1239 on 1021t is equal to ln, not ln, ln of 1595 on 1021. Dividing the ln to the other side, we get t is equal to this massive expression ln of 1595 on 1021 over 1 on 5 ln of 1239 on 1021. Typing that into your calculator, we get approximately 11.5 to 3 sig figs, so 11.5. Is it years? Let's have a look. No, it doesn't. Oh, yeah, years. All right. Number 3. A saucepan of water is heated to 95 degrees. The room temperature is a constant 23, and the water cools down to 55 after 5 minutes. The cooling rate is proportional to the difference in the water temperature and the room temperature. Blah, 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 blah. That's just a lot of information that just is going to help us solve A. Again, I'm going to talk to you about this in the next example. We've got to, in maths, and especially if you do bio or physics, you've got to realise and understand what part of the question is the information and what part of the question doesn't really help us and we shouldn't get too stressed about. So honestly, this part of the question, I don't really care about that. Doesn't really assist us in solving the question. It's good to know and it helps us understand Newton's law of cooling, but it doesn't really help us, so why stress about it? We've got to show that the water temperature, an equation, is equal to T plus 23, 72 e to the minus 0.162 T. So inherently, T is going to be equal to, we're only allowed to say our room temperature. That 23 is given, that's my room temperature. That's always the thing that's plussed on by itself, the room temperature or the environment temperature. Plus e to the minus kt, or e to the kt, pardon me. Right. We're now going to use my initial conditions. We know that saucepan initially has a temperature of 95 degrees. So 95 is going to be 23 plus a e to the 0, which is 1. So a is going to be 72. And that's good because 72 is what we were expecting. So now my equation is T is equal to 23 plus 72 e to the kt. Now we're going to use my initial conditions. The water cools down to 55 degrees after 5 minutes. So 55 is equal to 23 plus 72 e to the 5k, 5 minutes. If you can do this in one step, so e to the 5k, 55 minus 23 is 32, divided by 72, we get 4 on 9. So therefore, k, or 5k, is equal to ln of 4 on 9, which makes k equal to ln of 4 on 9 on 5, or 1/5 ln 4 on 9. Now we're hoping that's equal to minus 0.162. Let's double check. 1 on 5 ln of 4 on 9, and we get perfect minus 0.162. So we're basically done. Therefore, t is equal to 23 plus 72 e to the minus 0.162t QED. We're done. Find the temperature of the water after 30 minutes. All we've got to do is substitute t equals 30. So t is equal to temperature, 23 plus 72 e to the minus 0.162 times 30. What's that? It's going to be like 23 point something. 72 e to the power of minus 0.162. Now, I've stressed to you a lot, I don't like approximating that thing in the e power. I personally would never approximate up here like they have. But they have in this question, so I guess we can. But personally, I wouldn't do it because it decreases our accuracy. I wouldn't do it in the HSC. If we type that in, we get 23.56. Okay, when will the water temperature reach 30 degrees? Well, all we have to do is, instead of finding a temperature, we're now finding a time. So we're going to say 30 equals 23 plus 72 e to the minus 0.162 times time. I'm going to solve for t there. We're going to go 30 minus 23, divide 72. So 30 minus 23, divide by 72. We get what? 7 on 72. So e to the minus 0.162t equals 7 on 72. Taking the natural logarithm of both sides, you should hopefully be able to figure out that it's going to be ln of 7 on 72 on minus 0.162. So ln of 7 on 72 over minus 0.162, we get 14.38. Oh, 39 actually. Oh, one decimal place, 14.4, pardon me. So 14.4, now it's minutes. It's terrible. Show that the temperature of water approaches 23 as t approaches infinity. Number of ways of doing this. I personally would just say t is equal to 23 plus 72 e to the minus 0.162. I then substitute, say, in 100,000, and you get 23. Now, the reason that's true, we might want to state that. We might want to say as 72 e to the minus 0.162t approaches 0 as t approaches infinity. And that does make sense because it is an exponential graph. It's a negative exponential graph, and it looks something like that. So it's going to approach 0 as t approaches infinity. So those are the two ways of proving that. Both of them are logical ways of proving it. Okay, number 5, a bag of rice is taken out of the freezer at minus 9 degrees Celsius into the air of 25. The rate at which the meat warms follows Newton's law of cooling. To t is minus kt minus 25. Show that t is 25 minus ae to the minus kt is a solution of this equation, and then we're going to find the value of a. Right, so I would personally differentiate that. So to t is equal to minus k ae to the minus kt. So that's going to become a positive. So it's going to be positive k ae to the minus kt. Now, if we rearrange this question I just circled for AE to the KT, we plus the AE to the KT to the other side, minus T, we're going to get 25 minus T. If we then replace this with that over there, we're going to get to T is equal to K, 25 minus T. Now we're almost there, but you might notice we have to prove that this is kind of opposite, and we've got a minus K out the front. We're not going to stress though. If you take out a minus there, your 25 is going to become minus. Your T will have two negatives, becomes a positive, so we're done. Too easy. Part B. Oh no, we're going to find the value of A, pardon me. So, we've got some initial conditions. We know that it's taken out of a freezer and it's minus 9 degrees, which means when T is 0, T temperature is minus 9. So back into my equation, T is equal to 25 minus AE to the minus KT. We've got minus 9 equals 25 minus AE to the 0. If we solve that, we're going to get A is 34. We're done. Part B. My new equation now, before we have a look at the question, is T is 25 minus 34 E to the minus KT. Now in the question, part B, we've got the rice reaches 8 degrees in 45 minutes. Find the value of K. So we know that T equals 45 minutes and the temperature is 8. So 8 is equal to 25 minus 34 E to the minus KT. And pardon me, that's K times 45. So we're going to say, well, 34 E to the minus 45K has to equal 25 minus 8, which we know is 17. So that means that E to the minus 45K, well, 17 divided by 34 is a half, which would make K equal to minus 1 on 45 ln of a half. So we found the value of K, that's all we had to do. Perfect. So minus 1 on 45 ln of a half. All right. Part C, find the temperature that it reaches after 45 minutes. Another 45 minutes. So that would imply it's 90 minutes. So another 45 minutes would be 90 minutes. So my equation now after finding the value of K is 25 minus, we said that A was 34. Let me double check. Yep, 34 E to the minus 1 on 45 ln of a half, and we're timesing that by 90. So we type that in, minus 34 E to the power of minus 1 on 45 ln of 90, ln of a half times 90, and we get minus 111. I purposefully did this, and the first time I did this problem, I made this same mistake. So I wanted to show you in the video this mistake that I made. So when I do that, I get minus 111. Well, like, that doesn't make sense. How on earth could it be heating up and we get minus 111? Well, the reason is because K itself down here is negative. But when we substitute it back into my equation, K was negative in your equation. So if K is negative, and then you substitute K into minus K, it's going to become a positive. So it's going to cancel out. So we're actually getting rid of that minus there, and then you should get a nice answer of 16.5, I think. Yeah. Beautiful. Oh, that's C. So the reason I showed you the mistake that I made when I did this question initially was because in an exam, you've got to think about, does my answer logically make sense? Does it make sense for something heating up, being taken out of a freezer into a room that's 25 degrees? Does it make sense for it to reach minus 111 degrees? No, not a chance, so we made a mistake. Okay, this last example, the textbook's answer is wrong, so I pasted it in and then wrote it in what I would write. So we've got a chamber is 30 centimeters high, is divided into two identical parts by a porous membrane. The left compartment is initially full and the right compartment is empty. The liquid is let through from left to right at a rate proportional to the difference between the x level in the left compartment and the average level. Explain why dx dt is k 15 minus x. Okay, what's different about this question, and you're never ever going to be asked this in the HSC, you're really going to be given part B is where you would start. What's different is because we can't assume that we have this, and we're not allowed to differentiate this because we're not given it in part A. We don't know that yet. So we're going to verbally write down what's going on. So the answer in the textbook said that the average level of the liquid is 15. That part's correct. Well, and it makes sense. If you've got initially the left compartment being full at 30 centimeters, well, then the right compartment would be 0, and the average between 30 and 0 is 15. If it then fell by 1 centimeter, that would make the right compartment rise by 1. If it fell by 2, it would go to 28 and 2, and 27 and 3, and so on. The averages of all of those numbers is always going to be 15. So the question says that the rate is proportional to the difference between x and the average level. That's where your x minus 15 comes from. Now this part of the answer makes no sense because it's not actually answering the 15 minus x. So initially your dx to t is going to be this. And this is kind of employing like some biology knowledge, if you just think about it. If you've got liquid in a container and it's pouring out into another container through some sort of membrane, let's say it's coming through a cloth or some paper towel, well, initially the water is going to be very, very heavy and it's going to come out through the membrane very quickly. But as the water decreases, the weight in the left compartment is going to decrease. And since there's less water, that means there's less weight, which means it's going to slowly decrease. So the rate at which it's decreasing is also going to decrease. So that makes dx to t a negative number because the rate is decreasing. All the answer has done, or what we have to prove, is pull through that negative. So instead of x minus 15, we have 15 minus x. Part A, you're never ever going to be asked that in an exam. It's a ridiculous question, and you're never going to be asked that in the HSC, to the best of my knowledge, because it's not really maths. It's more like logically thinking about what a porous membrane does. Part B is really what we want to focus on, and the other parts as well. So show that x is equal to x is equal to 15 plus ae to the minus kt is a solution to this equation, and hence find the value of a, or not hence, find the value of a. So we're going to differentiate that, dx to t, and we're going to get minus k ae to the minus kt. But if we rearranged this equation for ae to the kt, we're going to get x minus 15. So we've got minus k, we're going to replace x minus 15 with the ae to the minus kt. So x minus 15. Pull that negative through, we're going to get positive k, then we're going to have a negative x and a positive 15. And we're done. That's what we had to prove. Now it also says find the value of a. So we've got my equation, x is equal to 15, no, was it 15? 15 plus ae to the minus kt. Right. Now, we've got to think my initial conditions. We know that t is obviously 0 at the beginning. X is going to actually be 30 because x is the height of the right compartment, and it says the right compartment is 30 centimeters tall and initially starts at full. So it's going to start at 30. So 30 is equal to 15 plus ae to the 0, which is 1, So A is 15, minusing the 15 to the other side. So therefore we've got x is equal to 15 plus 15 e to the minus kt. That's my equation. We're going to use that for part C or D. So part C says, what value does the level of the left compartment approach? Well, we're going to substitute, say, 100,000 into that equation. Now, if you do that on your calculator, you get 15. So the value is going to approach 15. Now, mathematically, that makes sense because this approaches 0 because it's a negative exponential. But if we think about it in terms of physics and biology, if you've got liquid coming out of a container naturally, well, it's going to equal out eventually, and you're going to have an equal amount of water in each side. Not a chance that the right compartment is going to get more full. You'd have to have some sort of pump for that to occur because of gravity. Okay. Now, part D especially is where the textbook is wrong. The answer is wrong. The level of the right compartment, so the right compartment level has risen by 6 in 5 centimeters. Now, if the right compartment has risen by 6, well, that would imply that the left compartment has also decreased by 6. So when the right compartment increases by 6, the left compartment, when t after 5 minutes, the left compartment is going to be the initial 30 minus 6, so 24. So x is going to be 24. Now the textbook for some reason lets x to be 6, which is completely wrong. So we're going to use our equation, x is equal to 15 plus 15 e to the, we're trying to find the value of k, minus kt. So we know that 24 equals 15 plus 15 e to the minus, t was 5, so 5t. Subtracting the 15 over, then dividing by 15, so 24 minus 15 is 9, divided by 15, we get 3 on 5. So e to the minus 5, not t, pardon me, that should be a k. E to the minus 5k is equal to 3 on 5. So minus 5k is ln, the natural logarithm of 3 on 5, which means k is minus 1 on 5 ln of 3 on 5, and that's the correct answer. The textbook answer is just wrong and it doesn't make any sense, so that is the correct answer there. Alright, hope that makes sense.